And finally, the last and one that's a little bit dear to my heart, we've actually been able to determine where the lander is in inertial space by measuring the two-way range of the communication signal between the deep space antennas on the Earth and the lander, and the time it takes tells you how far away that point is. And by measuring the Doppler shift, you can determine its location. And as it moves around its pole of rotation on Mars, you can then determine where the pole of rotation on Mars is. And the last time we did that was 20 years ago, where that pole has precessed around to there. And that tells you about the moment of inertia, the internal density distribution with depth. How big is the core and how massive is it with respect? And I can say proudly that on every single one of those science objectives, all 7, we have obtained new information that is really changing our view about Mars. If I could go to the video, please. What we've done is put together a little, I guess you could call it a tribute. It's sort of a 2-minute happenings of things that occurred on the 4th of July, and then I'll go through and describe the landing site.
Let us know if you see anything at all, please.
A week until it's coming in and out of the spectrum.
Roger that. Okay, we got a good storm sitting around.
Both very, very proud of your accomplishments, and the entire country is just reveling in your success, and we all congratulate you.
I haven't seen that yet.
Wow, a hill!
That's where the rover's going.
Okay, this is the landing site, and we'll pan around it. Here's the rover, our friend, trusty Sojourner, against our other friend, Yogi Rock. Here's Barnacle Bill. You can see we came off the rear ramp, back down, turned around, did a pirouette, got Barnacle Bill, went over, and after a few fender benders, got Yogi. We then proceeded back over this way. Here's Lamb. We got an APX soil measurement there. Here's Scooby-Doo, where we also got a measurement, APXS measurement, and we did a roll bar scrape test. We went behind the rocks Calvin and Hobbes here and came along to Mini Matterhorn, shown here, took a close-up picture, but did not waylay to get an APXS measurement, went over to my personal favorite, Mermaid Dune here, shown here, this dark sort of sandy-looking material. Here you can see the diving board that should have been the front ramp, but as you can see, it never went down to the surface. And so we preferred not to dive off to the surface and went the other way. And of course, again, as you've imagined, my favorite, the rock garden. This is what we affectionately call the bookshelf with these stacked up rocks. Let's see, Shark, Half Dome, Mo, and Stimpy here. Of course, the two hills, the Twin Peaks, which allowed us to determine where we landed on the surface in one day. And that was truly remarkable. It took Viking 1 year to figure out where they landed, and it took Viking 2 infinity. AKA, they still don't know where they wound up. And finally, after we get done going all the way around, we will then traverse all the way back to get an APXS measure of this magnetic target on the ramp, and then head north up that hill, effectively. Next, we put in a compilation of the rover movies that show our traverses and something about the way the rover moves on the surface. It has acumen steering so that all 4 outer wheels turn at once, so this vehicle can, in fact, turn in place without moving, in fact. Here's our fender bender. Well, we just missed a little bit, and we crawled up on it. Here we got it. You'll see we turn back, and the rover drivers nailed it. There's our APX up against Yogi, just as we'd hoped, avoiding the dice here. These are the rocks called the dice. We then came back towards us. We turned, and then we headed in a sort of a clockwise sense over to Scooby-Doo, which is that very white-colored rock that we saw. There's the APX on the back, solar panel, UHF link antenna. Here you can see we actually digging a hole with that middle wheel. And by looking at the deformed surface there, you can learn quite a bit about what that material is made up of. Here we're crossing the Cabbage Patch area just before Scooby-Doo, and I believe there's the APX going right down against the white rock or soil, whichever it is, Scooby-Doo. Here's our roll bar drag, what I call the Road Warrior rock wheel scratch test, where we take the little what are they, the snow cleats that you have back east, right? And we lock this one and use the others to deform and try to see whether this was cohesive material or not. You see we did absolutely nothing to it. That is very cohesive material. It's a cemented soil layer of some sort, a hard pan, if you will. Learning something, again, that is cohesive material. Here we go back. We made an attempt to get souffle. And this was sort of an iffy rock because it's just small enough that we didn't know whether we'd actually be able to get it or not. And this included a find rock command where the rover, using its autonomous sensors up front, actually, you saw the wheelie there? That great wheelie. First wheelie on Mars. There's souffle, which we attempt to get with our APX. And it's just small enough and difficult enough with this rock in front that we were not capable. We then doubled back and raced across our playa here, over the Cabbage Patch, past Scooby-Doo, off towards behind Calvin and Hobbes. We then stopped for the night, took a breather, and came around over some pretty rough terrain here. Look at us traverse that rock. It is a tremendous mobility system capable of traversing things twice the wheel height at least, if not better. We took a close-up image of the Matterhorn. There it is there. We're looking back towards the lander. Sorry, that's the tussle with Hasek. That was over. And finally, here's the, gee, this is going too fast for me even. These are the windsocks, which show you that we can image them in both without the wind blowing and the wind blowing to give you an idea of just sort of the motion, all the motion pictures we have. If I can have the first view graph, please. I'd like to now give you some idea of what the science is and what we've discovered. In a way of background, you guys have all seen this is our lander in the configuration that we never wished to actually see it, the exploded configuration. It has the cruise stage with solar panels on the back, 4 propellant tanks, a floating thruster cluster here, a back shell with 3 small solid rockets, a tetrahedral-shaped lander, and a heat shield. And every time I showed this prior to landing, everyone just looked at me and said, "You must be joking. This is clearly no way to get down to the surface of Mars." From entry here to the first bounce is 4 minutes time, and more than 50 pyrotechnic devices have to work perfectly to get this thing down to the surface. That includes parachute deploy, the cruise stage is already off, the heat shield dropping off, deploying the lander on a 20-meter bridle. Radar altimetry has to find the surface and return those waves. The airbags have to be inflated. The solid rockets have to fire. That tether is cut. This airbag then bounces and bounces and bounces, and 15 to 20 bounces later, it came to rest, sitting on the surface. The airbags were deflated by peeling away interior peel-away patches. The thing was opened and righted itself no matter which way, and finally coming to rest much, much later, a couple of hours. The extraordinary event about landing day was that we actually saw many of these events happen on the way down, which we were not certain of, and of course, as you know, we did pretty well. When we have the spacecraft on the surface in idealized form, it looks like this. Here are the four the triangular panels, the three with solar panels, the rover docked against one, the APX on the back of the rover, two forward stereo cameras, a stereo camera on the lander deployable on a mast, an able mast that comes up to a very good geologist's height, my height above the surface. So you can look around from up there. A low-gain antenna capable of tens to maybe hundreds of bits per second to Earth, and a lollipop shape, well, actually has a waffle pattern on it, high-gain antenna that points to the Earth. Meteorology mast here with a wind sensor on top, 3 temperature sensors, and the 3 wind socks. And what kind of mission is this? And if you're here, you've probably already heard me tell you that this is a rock mission. That's correct. Here is the Washington Post's edict on the Pathfinder mission, and you can see that Sojourner has found a rock, and it is very happy with that rock. Absolutely true. Completely oblivious to Marvin over here. So our goal then is to go find rocks. We are, my unofficial and a colloquial phrase for Pathfinder is roving for rocks on the red planet. Okay, where would you then send a mission that looked for rocks? Where would you go? What would you try to do? The landing ellipse, as accurately as we can target this lander, is in about a 100 by 200 kilometer football on the surface of Mars. That's a pretty big chunk of terrain. That's from here to San Bernardino and from Santa Barbara down to San Diego. And obviously Los Angeles would be a pretty poor place to land, given that we have mountains up to 14,000, well, 12,000 feet at least. We need someplace flat, safe, absolutely. If you don't land safely, you get no science. And the best we could do was look at this area and observe things about the size of rose bowls, full football stadium-size objects in that ellipse. We chose, for a number of reasons, to place this ellipse at the mouth of a giant catastrophic outflow channel known as Aras Vallis. This channel carried the water of all the water in the Great Lakes in about a 2-week period as it carved this thing in truly catastrophic fashion. If Noah was on Mars, he was riding on top of this wave. It carved this channel. It's 60 miles wide by 1.5 miles deep, and it carried all of these rocks out to our landing site to look at. This is a catastrophic floodplain, if you will, a delta, where all this material was brought. And the rationale and the idea is that here's a place where we can go, and in 1 pixel on the next slide I'll show you, we may be able to see a whole wide variety, a diversity of rock types on Mars. And since we know absolutely nothing about, well, almost nothing, about what Mars is made of, that seemed like a good place. Can I go back one just for a second and show you that the area that this drains, can I go back 1 slide, please? That this drains is ancient heavily cratered terrain. You see all these craters? They're edge to edge here. This is among the most ancient terrain on Mars. It likely dates back from 4.6 to 3.5 billion years. And so the idea is, by looking at this location, we could see a potpourri, a smorgasbord of different rocks from the ancient highlands to try to understand how the planet differentiated and whether or not, if we were very fortunate to find a sedimentary rock at the landing site, what the early environment on Mars might have been. Was it, in fact, warmer and wetter? And could it have been more like the Earth at that time? And could it, in our wildest dreams, have actually supported life, as the Allen Hills meteorite 84001 suggests? So that's the rationale, that's the logic, and that's why we went here. Now, if we can go to the next one, I'll show you the sum total of the imaging data. This is the best data we had prior to landing. Here's our 60-mile by 120-mile ellipse, and we're looking at bumps that are the size of football fields, okay? And they asked me, the engineer said, Matt, where's a nice, safe place to land? And they're concerned about things on the size, the scale of this podium, a meter size. And all I have to work with is things that are football field size. So you can see the problem right away. We used a whole variety of remote sensing techniques. We bounced radar waves from the Earth, from here. We looked at thermal inertia data. We looked at color data. We analyzed the slopes on these bumps and these hills, and we basically said, as far as we can tell, this looks as safe a place as anywhere we have on Mars. And it's a really neat place geologically because it carried all this material down in the flood. You can clearly see these streamlined islands carved by this flood and deposited this material in this nice flat plain. So the prediction is that this is a depositional fan. We predicted that the number of rocks, the abundance of rocks would be something like Viking 2, about 20%. And we also predicted that there would be less dust than Viking 1, where it took them 1 year to find a dark-colored rock on the surface. And that's obviously bad if you want to measure the composition of rocks and not the composition of dust. Okay, well, you've all seen this. This is where we landed, and that is backwards. I can tell because I know which of the twin. Can we flip this, please? Thank you. Ah, much better. There's Twin Peaks there in the right configuration, the tall one to the south, the low one to the north. Here's our beloved rock garden, Wedge, Shark, Half Dome, Moe, and Stimpy. Here's a very big rock out in the outside. We landed, we took this picture, and we saw these airbags obviously impeding the release of the rover ramps on either side. And these ramps are spring-loaded, so if they were to be deployed here, they would hit that bag, come back, and damage our baby, and of course that's a no-no. So we had to pick that pedal up at about 45 degrees. That one's backwards too. It looks like they're all backwards. And retract the airbags further to get that airbag material out of the way before we could then deploy the ramp shown here with the airbags just out of the way. Some of it's even tucking up here before we could get down to the surface. There's our friend Barnacle Bill. And get down to the surface we did. We rolled right down. You can see the flower-like consistency of this drift material by the look of the rover wheels that we caused in it. There's Yogi. These are all backwards. You're going to have to flip every single one. That's backwards. That's Barnacle Bill. Can we flip this one? There's Yogi. Now it's back. See, we drove backwards off. There's Barnacle Bill. There's the windtail. There's Yogi. And these are the flats that we came upon. And it almost looks like water was kind of sitting here after the flood, and as it dried up, it formed some of these kind of ring-like things. But that's really speculation. Okay, here is the full panorama. Prior to deployment, you can see there's all this hardware in the way. The imager is down at about the level of my knees right now before it's actually popped up to its good geologist height. And it looked at the scene and we said, yeah, that's a very rocky place indeed. And then when we actually popped up, I'll get to that next. Here is what the landing ellipse did in the final few days prior to landing. As the nav team refined their targeting predictions, here's our big science ellipse, our 100 by 200 kilometer. It was saying that we were further down like this, and we were up until all hours of the night on the 3rd and actually up until 2 a.m. on the 4th, measuring the slopes on these streamlined islands to decide if that was a dangerous place to land or not, given that, that's a sort of an obstacle there. And cooler heads prevailed. We did not do anything, and we landed very, very close to the center of the ellipse. The navigator. Well, we'll show you. We'll just relax. Here's a blow-up of where the nav team put us in this stream of secondary craters, which are pointing in the direction from which they came, which was to the south. Here's a boulder bar behind this obstacle to the flood, and we wound up right here. And the reason we know that is that this peak here is the only peak with twin peaks that's in this entire region. And one of our science team members saw this, predicted that we had landed here, and predicted that we would see this crater to the south prior to seeing it. Truly masterful. Here's where we were. We've now located ourselves with a whole variety of things. Here's the Twin Peaks right here. There's a knob to the north. There's the far knob, and the so-called Misty Mountain, and another knob here, and here's the big crater. And there's even a rim shot crater that we've seen in close-up on the edge of it, and they all indicate that we know where we landed to within 1 pixel. Truly remarkable. Okay, when we did pop up on the mast, And this is backwards too. Every single one of these needs to be flipped. Here's Yogi. There's the Twin Peaks. And all of a sudden, it doesn't look so rocky anymore. Now you're up at a decent height, and you're looking down on things, and there's plenty of space in between. Lots of soil areas. There's Bonneville Salt Flats here to do your NHRA drag nationals. We looked in a little more detail. Here's the meteorology mast here. Here's our dark-colored Mermaid Dune. The low-gain antenna is shown here, and the diving board for the wrong way ramp there. Here's the Brock Garden. Here's Wedge right here. We have actually gotten an APX measurement just in the last handful of days here. We are now sitting with one wheel on top of Wedge, about to head off in this direction towards Shark. These are what we call, or what many of us believe to be imbricated blocks, where these are stacked and tilted in the direction of the flood, where the water came from left to right. And they're sort of tilted in that direction and are very indicative of high-speed flow and deposition of rocks in this catastrophic flood. And when we look around, we see effectively everything looks consistent with this catastrophic flood interpretation for the deposition of this. Big round boulders perched upon the surface. How could they be there any other way but to be carved? And when you look in carefully around Yogi and even Barnacle Bill, there are moats where that rock was deposited first and late-stage water carried away the fines beneath it to leave that in its own little moat there. Here it is on Yogi, and the so-called band between what looks like less dusty material and more dusty material. Look at the rover wheels here. They're completely dust-caked, completely covered with dust, and yet when we took an image of the rover less than a day later, they were completely clean, implying that the dust is electrostatically charged and is attaching itself to the wheels. And it also looks, which is truly remarkable, that this is a lighting effect. The sun is coming this way. We're seeing direct sunlight on this side, and 40% refraction of the sunlight in this salmon-colored Martian sky is producing a red tinge on everything else you see from the scattered light. When we look closer in the color pan, we saw disturbed soil zones here and here and up here, which actually mark the regions where this spacecraft bounced before it came to final rest. And it actually bounced. We see about a dozen of these, or maybe about 6 to 10, I would say, on either side of the site before it actually came to rest. This is not a spherical ball. It's not completely, the density distribution is not round, and can I have the next one, please? There we go. Again, more disturbed zones. It looks like this rock has actually been pushed by that here. It used to be sitting back there, and you see, again, more disturbed zones indicating the final bounces of this spacecraft. And finally, the very last bounce before landing was right here as it rolled off of Mini Matterhorn and onto its base pedal just before landing. Next one. Okay, when we look at the site, I think that's backwards too. It looks wrong. Can we flip that one? Yeah, that's better. You know, you look at these so much, you actually know which way. That's the only thing I can tell you. What's shown in red here are large, rounded, and somewhat dusty rocks. And we believe that these are likely rocks carried by the catastrophic flood, making them a little bit more rounded than these dark and angular and smaller rocks that appear much cleaner and less dust covered. And the interpretation here is that these big things are all carried by the catastrophic flood and deposited. They've been sitting on the surface there for 2, maybe even 3 billion years gathering dust. And these things may be ejecta from that nearby crater to the south, for example, or others. And so these are cleaner. They came along much later after the flood, and they're sitting there in a little bit more pristine shape. In addition, you see this very whitish material, like Scooby-Doo and others, which indicates a very white material, which is very unusual and not at all what we expected. When we look at the color variants, you can see there's this dark soil material here, there's this reddish soil here, there's black rocks, and there's this bright drift material. And they all have different reflectances at wavelengths in the visible between 0.4, the deep blue, and 1.1, the near infrared, red being sort of in here. And there's your maximum red. That's why Mars is red, because of this difference right there. False color really kind of shows you the aeolian activity, this wind tail behind Barnacle Bill, where the wind is blown in this direction, consistent with the wind tails we saw from the orbital images prior to landing. Now, we do have this wondrous little rover, and it can, in fact, take a picture of us. Well, our computer, anyway. How's that? And sitting inside here, this is the lander with the airbags sort of bunched around. Here's our trusty ramp we came down. Barnacle Bill is shown right here, and you can see the hardware. There's the high-gain antenna. The IMP has been deployed on the mast, so it's sitting up here, and so on. Next one, these are the dice looking off towards the rock garden, and there's the lander with the ramp. Here's Yogi. You can see in the shadows that there is this sort of moat, this deep here, and this rock actually comes to a point here. It's actually sitting almost on a dime. And after we looked at it from another geometry, we said, oh, great, Yogi squashes Sojourner on Mars. Fortunately, that didn't happen. Here you can see one of these trenches dug by the rover wheels. We actually rammed and pushed this rock, and you can see some of this material has cohesion. It's sort of cemented together because it breaks off in these clods, if you will, whereas other material appears much more fine-grained and breaks more easily in the rover wheel tests. Here's our air hole for the lander. There's the high-gain antenna, and there's one windsock showing it right there. And again, the aeolian activity that sort of sculpted this surface well after the flood. Again, a look off. Here's looking at Pooh Bear, and this is Mermaid Dune, where you can see it's actually sitting above the surface, and we went in here and did a whole series of soil mechanics experiment. Here we are. We got Barnacle Bill, as you know. There's the wind tail. There's the APX placed right up against, or as I think I said, kissed affectionately, Barnacle Bill. And here it is against Yogi. You can see we've got the APX right up against it. We also got Scooby-Doo and a variety of other soils. And when, oh God, a bad chart. This has got numbers on it. Okay, how about just look at silica? That's the only one you have to look at. You can see that the soil has about 20% silica. Silica is the second most abundant element on the Earth after oxygen, and it is the dominant thing that makes rocks. And you can see that Barnacle Bill has a higher percentage of silica, almost 26%, compared with Yogi and the soil. When we put these elements into oxides, in this case a normative quartz, if you will, SiO2, you can see that the soils have 43 to 46%, and boom, Barnacle Bill has 55% silica as compared to something more like 50. And if you just do nothing more than compare that with the composition of the continental crust on the Earth, you see that that's not a bad measure. Here's Barnacle Bill, 55, and here is the average continental crust and sediments, very, very different from the oceanic crust, which is much more silica poor. And finally, that the SNCC meteorites, the so-called rocks that we already have from Mars, have a silica abundance that is lower and required to make soil. So we have a new rock type on Mars, and it's a very silica-rich rock type, which implies that you need much more higher-order differentiation products on the red planet, perhaps more akin to the kind of differentiation we have here on the Earth, rather than the very primitive differentiation that we have not had on the moon. And I think we'll skip these next ones. Let's just kind of go through these. Keep going. Well, leave that one for a second. Here, if you take ratios of calcium to silicon and iron to silicon, you see these mafic rocks, the very primitive rocks on the Earth, the andesites, which have higher silica content, and the rocks we've measured on Mars indicate more like the terrestrial, as opposed to all of these red meteorites that we have on the Earth that we're very, very confident came from Mars, the so-called SNCC meteorites, named for Shergatti, Knocklite, and Chassigny. SNCC, S-N-C, right, that's it. And the Viking soils that we measured. And the soils we measured at Pathfinder are very similar to the Viking soils, implying that whatever soil formation mechanism we have on Mars, it's in fact global in process. You form it all over the planet. It's likely related to the wind-blown dust that we have on the planet and solidifies from that. Let's skip that one. Keep going. If these are volcanic rocks, Very primitive basalts, or very primitive rocks are called basalts, and they are the first melt that you would get if you simply caused a primary melt at the top of the mantle. That liquid came right up through the crust and froze at top and didn't do anything else to it. That would be a basalt. All of our ocean basins on the Earth and all of the lunar lowlands, the Mare basins, are made of this kind of material. And here you see we're getting measures of things that are much more silica rich, implying a much higher order differentiation products. The only food analogy I can think of is unhomogenized milk, where the cream actually goes up to the top. So the lighter elements are going up high, the silicon and the oxygen, and the heavier elements, the iron and the magnesium, are sinking down. Sounds like one unhappy kid there. Let's keep going. You guys don't want to know about normative basalts. Here we have Martian soils. You can handle this one, I think. Here are the Viking measurements here in these big bars. You can see how much error and uncertainty there is in the Viking measurements for soil. This is all the soils. And you can see the soils are remarkably similar almost everywhere we've measured them. The Pathfinder site is 800 kilometers from Viking 1 and thousands of kilometers from Viking 2, implying again that whatever process makes this soil does so on a global scale. Okay, here's the Earth. We tried and we tried and we tried, and all we got was clouds. But those clouds were pretty darn neat. If the Earth was there, it would be a little blue speck right there, and we saw these tremendously interesting and complex wispy clouds in the atmosphere of Mars just prior to sunrise. We're actually looking, the sun is actually over the limb here on the other side, and we're just seeing the reflection of those clouds on the surface. In the red, they are reddish-orange, the clouds are a little bit white, and the sky is this salmon-colored pink from all that red Martian dust. A sunset on Mars, you know that because this is Twin Peaks and that's to the west. And there's the sunset. And we have an astronomical observatory on Mars. This is Deimos, seen from the spacecraft. We've tried and tried and tried to get Phobos to no avail. This is about 3 pixels in the imager, and you're really seeing the point spread function of the camera here. But it is remarkable that you can see stars at night and the satellites. The profile, the temperature profile, as we came in through the atmosphere with Pathfinder, is shown here, 160 kilometers down to the surface. Here's the temperature. Shown in red is the Viking observations here, and in blue, the Pathfinder ones here. And what you see at about 60 kilometers altitude, Pathfinder is quite a bit colder in the uppermost atmosphere than what Viking measured. But down below that, they're really not that different. They look pretty darn similar. The one possible interpretation is that Viking entered the atmosphere at 4 p.m. local solar time. So you'd expect the uppermost atmosphere to be warm. We entered at 3 a.m. local solar time. That's about as cold as you can get. And one model is that this difference, this 10 or 20 degree difference between the temperatures seen by Pathfinder and Viking are in fact the difference between entering in the middle of the night and in late afternoon. These are the accelerations of, I don't think that's quite 15, but you get the idea. Notice that depending upon the way this thing bounces, it actually increased in bounce. Subsequent, this one's probably 40 feet or so height, well over this building. And when you look at the pressure sensor on board, you actually see the pressure sensor measuring those variations. And notice that the pressure here is higher than the pressure here. And so this thing bounced downhill, which is good because this is a billiard ball or a bouncing ball, and you would think it would go downhill towards potential energy. Here's the pressure measured on Mars. This is the Viking curve. Here's Pathfinder shown here in red. And what you can see is we've gone through our barometric minimum here in late northern summer, which means that the South Pole is at its largest extent with white ice all over, or carbon dioxide ice all over the surface. And now as we enter into northern fall and autumn, that polar cap in the south will start to shrink. Here's the pressure in millibars over one solar cycle here. And what you see is there's 1, 2, 3, 4, 5 pressure maximum, which is very, very distinct from here on the Earth, and it's consistent with having mixing of dust within to the upper 60 kilometers, producing these higher order diurnal products in the pressure sequence. Finally, what we call the presidential Met sequence here, when we looked in the morning, this is early in the morning on Mars, we saw these enormous, enormous temperature changes on the surface. Look at this. It's almost 20 degrees, 15 to 20 degrees temperature variation within seconds. Okay, well, 30 seconds. How's that? That means if you were standing on Mars and you were standing there, a 40-degree difference in temperature, if you could be there without a spacesuit, which of course you can't, but if you could, 40-degree temperature shift in about 30 seconds' time. That's pretty wild. And if you were standing there, your feet would be warm. Sorry, did I get that backwards? I sure did. Your feet would be... Wait a minute, that doesn't make any sense. Your feet would be warm. It's up here. See, I told you. And your head would be cold. There's another 20. That's almost 40 degrees Fahrenheit between your feet and, well, not quite your head, but just about here. So you're standing there, and you're freezing by 40 degrees, and your feet are warm, and your head's free. And so this is like a bizarre place. And there's obviously nowhere else on the Earth that has these sort of atmospheric variations. The interpretation is that in the morning, the surface is warmed, it's captured the heat, it's held it there, and there are these wild eddies, turbulent eddies, coming off the surface. The air is warming at the surface, and it's convecting up and going sideways in this way and that, and, well, you kind of get the idea. In addition, we have devils. We are still not sure if they're dust devils. Okay, come on, guys. A dust devil is something where you have winds that spin around. You guys have all seen Twister, but this is a little bit smaller scale, obviously. You have warm air in the middle, and this thing moves sideways. And if you had this go by your spacecraft, you'd see the wind speed peak in one direction, you'd see the pressure decrease in the middle, and then the wind speed would peak in the other direction. We have now captured a few of these with our atmospheric sensor. What's shown here in blue is the upwind wind sensor, which measures a peak in winds here. Low is a peak. We then get a trough in the pressure sensor, which is the black bar, and then a peak on the other side wind sensor. And so we've seen and actually felt dust devils on the surface of Mars. We have not imaged them yet, so that's why I said we don't know if they actually have dust in them or it is just simply an atmospheric disturbance. We will try to do that. The prime time would be sort of in the late afternoon. I think that's it for the slides. Could I just have the lights on? Just then, as to what's next for Pathfinder, we now are going from this sequence where we've tried to learn everything we possibly can about the landing site. We've taken what we call the super pan, where we've gotten every octant of the entire suite all the way around us in lossless 3-color stereo and 9 additional colors. Effectively a tremendous data set that we're bringing back slowly day by day. Now, once that's done, you've kind of imaged everything around you as good as you were ever going to image it. And so the next phase is to sort of go on to a monitoring phase. What happens to the temperatures on Mars as we go into autumn and the winter? And so to try to do that, we no longer have a battery on the lander that keeps us alive every night. We have to choose which nights the lander will stay alive all night. And we're doing that every 10 or 12 days into the future so that we can try to record the full diurnal temperature cycle and meteorology at the surface all the way into the fall, and if we're very fortunate, into the winter as well. In addition, we hope to continue to measure where the location of our site is to much, much higher accuracies. And we think we can get it down to meters, pretty remarkable, from the Earth to Mars, to meters, to determine where the pole of rotation is and how much mass is within the center of the planet, how big the core is, whether there's a metallic core, and how large it could possibly be. And then finally, for the rover, we've gone all the way around the lander clockwise because we couldn't get into the rock garden the other way. Now we'll go all the way around the lander in a counterclockwise sense, stopping at Mini Matterhorn, and we'll go back to Mermaid Dune, such a nice place, and go all the way around and look at the magnetic target on the rear ramp to determine the composition of that magnetic dust. And then we'll go north up that hill, which is the only direction all the way around the lander that we can go and maintain visual communication with the rover. And that means that we would maintain a UHF link, so we'd always be able to tell our baby where to go and go up that hill and look for more rocks and more samples of things to get. So that's sort of the long term. I hope I have this job for at least another year, and we hope that Pathfinder will last as long as it possibly can. Thanks very much.